Alright, CNT125, Chapter 9, routing protocols. We're now going to look at some specific routing protocols, and many of these we're actually going to hook up and work with in the lab room. Just giving you a heads up. With our routing protocols, there is administrative distance associated with the data that protocol gathers, the routes that protocol gathers, and it actually will put that number with that routing protocol. So as we look at the routing protocols here in the next section in our lab room, as we start seeing a EIGRP route, if you will, that's going to have administrative distance of 90, which is, I'm using little air quotes, that information is better than OSPF that's 110, which is better than the information ISIS gathers, which is better than, 120. The quality of that information, if you will, the reliability of that information, if you will. So keep that in the back of your brain as we start looking at these routing protocols. All right, routing protocols come in two major categories, interior and exterior. Interior are the routing protocols used, like inside of your company, the core routers inside your company. There are distance vector, link state, and hybrid. We're going to look at that in just a minute. Some distance vector interiors are RIP and RIP version 2. Link state would be OSPF and ISIS, and hybrid would be EIGRP. These are mainly the ones we are going to work with in the lab room. Exterior gateway protocol, the main one that's out there is BGP. This is the kind of thing your service provider would be using to route traffic from blah university to blah university, blah company to blah company. That is what your service provider is using. So here they're showing you inside your network, you might be running RIP, OSPF, ISIS, EIGRP, and then out in the internet backbone in your service provider area, you would be running BGP. That sort of thing. All right, so let's take a look at distance vector routing protocols. Distance vector, they calculate best path based on typically just distance. How many routers away? How many hops away? That's typically the only factor they use. Some will add in latency, maybe traffic, but usually distance. How many routers away? And as we know, it's kind of like saying, hey, how far is it? Well, it's only 4 roads. But what they're not telling you is that one road you're on for 9 hours while you're driving, driving west through Montana or something like that. I'm on that road for 9 hours. That's the piece that's not factored in typically for distance vector routing protocols. They periodically exchange the entire routing table, usually time triggered, every 30 seconds, every 90 seconds kind of thing. And it literally shares its entire routing table. It's like, here's all the routes I know, here's all the routes I know, usually by a broadcast. And because it's by broadcast, as one router broadcasts to the next one, that next one's not going to pass that broadcast on. It'll pick that information up, add it to its table, turn around, then broadcast its table out, and so forth. So they tend to call this routing by rumor, because you're literally just taking your neighbor router's word for it. Okay, those are the networks you got on you. Okay, great. And then on to the next one. Okay, that's what you got. Great. Okay, on to the next one. Distance vectors tend to be very slow to converge, and potential for persistent errors. Link states, OSPF, ISIS, they focus less on hop count and more on the state of the connection. They tend to factor in a few more things about that link, kind of like what you do when you're deciding which way I'm going to drive to work. I factor in the type of road, the time of day, whether it's construction, and then I make my decision kind of thing. They usually send their information typically by multicast. The difference there is when you multicast, you're actually trying to send all the routers at essentially, I'm doing air quotes here, at the same time. The information gets out to the routers much more quickly. The routers factor that, then turn around and say, okay, with that information, I'm going to update my table in this way. The routers then build their own table. This does require more router processing, literally more processing on the router to do this. Typically, these updates are sent only when a change occurs. Now, you might see little hello messages where it's talking to its neighbor, but the legit routing table updates typically only occur when a change occurs. Kind of like if you're listening to the radio for traffic updates, they typically only come in and tell you when something changed. They don't come in every 30 seconds and say, hey, blah highway looks great. Blah highway looks great. They don't typically do that. They typically only interrupt when there's a major change in the roadways. So your link states are usually very scalable for large networks. Your distance vectors are not. Hybrid usually tries to take kind of like the best of both worlds. You'll see some pieces of both. EIGRP is the main hybrid that we're going to look at. It's actually going to try to, it kind of functions as a distance vector, but it kind of pulls elements in from your link state, syncing information across the network a little more quickly. All right, so let's take a look at each one of these for just a minute. So RIP, Routing Information Protocol. This is an interior gateway distance vector routing protocol. It's only going to factor hop count. It's going to broadcast this table every 30 seconds, no matter if there's a change or not. This is going to create a lot of overhead. It's slow to converge because you have to broadcast the neighbor, then they have to broadcast, then they have to broadcast. So it might take, a minute or two for information to traverse through the network. Because of that, the hop count's limited to 15 to prevent these routing loops. So this does not work well in large networks, and that's why I think the book even calls this a legacy protocol. Yeah, we'll hook this one up first just to see what it does, and then we will move on to the other protocols. Here's a sample routing table with RIP. Here's the directly connected route, and then here's the route that RIP learned. If I take a look at that line, I copied it here for you. If I take a look at that line, R says it's RIP. 172.16.0.0 is the network it learned. 120/1, 120 is your administrative distance. That's the reliability of the RIP information. /1 is one router away. And I get there via this IP. That's really the IP address of the next router. And I go out this port to get there. So there's your RIP routing table and very simplistic nature of what it is. Our link state, and we're going to work with this one as well. We'll take RIP off and put OSPF on. Open shortest path first. This is my link state. It was introduced to try to make improvements to RIP. This is going to support larger networks. It uses a little more complex algorithm. Uses a cost metric based on the bandwidth of the link. So the higher the bandwidth of the link, the lower the cost, lower the delay, if you will, the lower the cost of going across that link. And the cost is usually a summary of all the bandwidths to get to that destination network. This is going to demand more memory and processing on the router. So it typically uses routing updates that are multicast out when a change occurs. Again, you might see some hello messages from time to time, but those are not major routing updates. The major routing updates will be multicast between the routers. And because of all this, it's going to be much faster to converge and a lot less overhead on the network. Downside is it's limited to IP4 networks only. IP4 networks only. Here's an OSPF routing table. Again, if you look at the O line here for OSPF, here's the network. 110, there's your administrative distance. Notice that's better than the 120 of RIP. 11, there's your cost metric. That's the cost it has factored in for the bandwidth of that link. And obviously, the lower that is, the better the quality or the better bandwidth of that link to get to the destination. This is the next router we're going to go to get there, and I'm going to go out this port to get to it. There's your OSPF routing table. Again, we'll put RIP on. We'll work with that, take that off, put OSPF, work with that, and then we'll move on to our next protocol. ISIS routing protocol, intermediate system and intermediate system. This is again another link state. It's similar to OSPF. It's designed for use in core routers. And it actually does adapt to IP6. So this has become a little bit more preferable for service providers because of that functionality, and it's more scalable than OSPF. Here's an OSPF, or excuse me, here's an ISIS routing table. As I look over here, 10210, there's your destination network. 115, you'll see that is kind of in between OSPF and RIP as far as administrative distance. There's the cost metric again. I'm going to hit this router to get there, and I'm going to get this port to get to it. I'm going to go out that port to get to it. EIGRP. After we work with OSPF, we're going to take OSPF off and put on EIGRP. This is our hybrid routing protocol. Developed by Cisco, and it's kind of a hybrid of distance vector and link state. It is fast to converge, has low overhead, a little easier to configure than OSPF, which we'll find. It's pretty much kind of plug the networks in and go. It supports large networks, capable of connecting multiple vendors, but still pretty much optimized for Cisco. So if you have an entirely Cisco network, this might be the one you use inside your network. And again, the metric is a composite metric. It's going to use 5 metrics: bandwidth, load, delay, reliability, and MTU, to combine them. And it actually has a very sophisticated formula it uses to calculate those together. But the result is still the same. The lower bandwidth will yield a higher metric value. So the lower that metric is, the better the bandwidths, the combination of all those things, the better the bandwidths and everything to get to the destination. So that number, the lower that number is, the better that route is. Here's an EIGRP routing table. As I see over here, D, that is indicating, I look up top up here and we see D, there it is, EIGRP. So 170/70 network. Here's your administrative distance, 90. You'll notice that's better than all the other ones we looked at so far. And then here's that composite metric, 30,720. And that is the composite of all those things we just mentioned. Bandwidth, load, delay, MTU, etc. On the link to get there. I'm going to go to this IP, this router, if you will, out this port to get to it. And there's your EIGRP routing table. That'll be the last one we put on our network to look at. BGP, this is the basically your service provider protocol. Be familiar with this one. This is the kind of thing that the provider is doing for you. This is designed to move traffic between networks, saying, hey, to get to this, go to this IP to get to all these networks inside. You know, all these networks in the hack network kind of thing. So as I look at the BGP routing table, I might see this destination network. Here's your administrative distance 20 cost, and then I'm going to get to that network via this IP. Once I go to this IP, I can get to these this network and/or these networks inside, if there's multiple. When we work with routing, we might have some redundancy we need to factor in. So the book introduces active-active redundancy and active-passive redundancy. Active-active is all redundant resources are active all the time, and it might actually load share between them. Active-passive, your redundant pieces might be sitting there in a state waiting to kick in when it needs to. So they could be configured in more than one way. Where I would typically see this is having more than one ISP connection for a company. So if I have more than one ISP connection, I need a protocol working between the routers to make them work in tandem. And I would run into these. Virtual Router Redundancy Protocol, Hot Standby Routing Protocol, or Gateway Load Balancing Protocol. Let's take a look at each real quickly. What these are designed to do is if I have 2 routers connected out to an ISP, the protocol is designed to make them look like one router to the outside world. So that protocol is going to advertise this IP as the outside. Even though there's 2 routers, it's going to advertise that IP outside so the rest of the world sees one router even though there's 2 inside. And that's going to be the function of that routing protocol. Hot Standby Routing Protocol, same thing. It's going to work very similarly. This is a Cisco proprietary one. And here again, inside, the protocol is going to make these 2 routers work in tandem and advertise this IP as the outside IP, this IP out here. So these 2 links out here look like one link to the rest of the world. And Gateway Load Balancing Protocol, here I could have multiple. Here I could have multiple acting in tandem. They're individual inside, but outside they all appear as one single IP address outside, one single connection, if you will, to the world. So as you have a company resource connecting to ISP, you might literally have 2 routers or 3 working together to move traffic in and out. But from the outside world, little air quotes here, it sees one router, one connection going into that company network.